Okay, maybe before we start, and we have about 2 minutes, I'll say some words to clarify the status of our meeting, because we have some new participants and some old participants. Actually, this is one of our regular scientific seminars of our Quantum Technology Center of Moscow State University, where we invite our colleagues to present their scientific results or give review talks. But today we start a special series of our meetings, which corresponds to our BRICS collaboration project between School of Physics of National Laboratory of Solid State Microstructures Collaborative Innovation Center of Advanced Microstructures in Nanjing University, the group of Professor GIQSUL Ma, the Department of Physics of Federal University of Santa Catarina, group of Professor Paulo Ribeiro, and our Quantum Technology Center of Faculty of Physics of Moscow State University. So the project is dedicated to multi-photon and high-dimensional platforms for photonic quantum information processing. And today and next week, at the same time, we have the first 2 talks in this special series. So next week, Professor Ma will tell us about harnessing single photons in quantum technology. And now Professor Paulo Ribeiro will tell us about quantum thermodynamics and phase conjugation with structured light beams. So we will have about 1 hour for the talk and 30 minutes for questions and discussions. So the rules of our meetings: if you want to ask somebody something, you need to raise your hand. We have this option in Zoom meeting. During the talk, you may raise your hand and ask some short question if it's necessary. The most of questions will be at the end of our meeting. And also, if you haven't microphone or you can't ask your question directly, you may write it in the chat. But it's better to raise hand and ask directly, because I may miss something in the chat. If somebody wants to ask the question from YouTube translation, it's also possible using YouTube chat. So I think.
How do I raise a hand virtually?
Okay.
I have a question.
Yeah. Yes.
How do I raise a hand virtually?
It is possible in Zoom.
If you click to participants on the top, that is raise hand.
Yeah.
Right.
So okay. Okay. So now I will turn off all the microphones except speaker. I try to do it. Oh, okay. I think everybody can do it himself. It's better. So yeah. So please, you may start, I think.
Thank you. Okay, so good morning, good afternoon, good evening, everybody. So I would like to start with some acknowledgements, right? But the first acknowledgement goes to Xiao Song, who told us about this opportunity for this call, BRICS. And second acknowledgement goes to Sergey, who joined us in this project. And third acknowledgement goes to Sergey team as well for organizing this virtual meetings. I think it will be a very good stuff for all of us. And I would like to say on behalf of my team in Floripa, the Brazilian team, that we are very happy to participate in this project. Even though we still haven't earned some money, but it's already good to be part of this collaboration. And then, of course, we have acknowledgements to our funding agencies that you can see here on the bottom this first slide. Okay, so my idea today is to start just introducing you, to telling you a little bit about this research group in Florianópolis, Santa Catarina, where it is, and who we are, very quickly. And then I will fly over two subjects that concerning a recent subject in our group. And so if you are interested in details, then please tell me in the end, or we can talk later. But I'll try to give you an overview about these topics, so that you can have an idea of what we are doing, and this may help us to identify points for future concrete collaboration in this project. Okay. All right. So just to give you an idea, this is South America. Brazil is here, and here is Rio de Janeiro, probably the city that you all know, you heard about someday. And this is the state of Santa Catarina, where we are. And there's a city called Florianópolis that I show here in the Zoom. Is an island, in fact. And we are here in this island. It's the capital of the state of Santa Catarina. And I was previously in the University of Rio de Janeiro, and I moved to Santa Catarina in 2015. So it's a relatively young research group. They are still building things, but then the city is in an island. The name of the city is Florianópolis, and we like to call it Floripa. It's a more simple way to talk about the city. And if we look closer in the island, we see this triangle here, this region, which is the Federal University of Santa Catarina. This is a picture showing part of the university. Is a pleasant place. It's a very nice place. So I hope you come to visit us very soon, when it's possible to travel. And the city of Florianópolis, or Floripa, is a really beautiful place, a very pleasant place. The whole island. We have more than 40 beaches like this, and I like to show this to collaborators to make them want to come and visit us, because it's really a nice part of the world. Here's a view of the island, a picture. Very good. This is a picture of our group. We use this acronym GIQSUL, which is in fact about a group of quantum information in the south region of Brazil. And this picture must be updated. Some people has already left and some new people came, but we were not able to take a new picture. But I would say that 80% of the group is represented here. And this shows that we have a considerable group of young people really working hard, interested in doing nice physics. And here are some names, and we like to cooperate. So it's important to say we like to cooperate first with our own theoreticians here in our institution, like Eduardo Buzioni, which is our the theoretician in our group, the leading theoretician. And lots of people in parts of Brazil and in the world, so we can have a long list here. So really like to cooperate. So I think we have a good possibility that we can do something together. These are pictures of our lab. So we are building these things in the last 5 years. We have 2 optical tables. I will say a few words about what we're doing these optical tables. Relatively simple things in terms of experimental stuff, because it's been hard to get funding in Brazil, especially in the last few years. But anyway, we are doing some things, and we have essentially 3 types of experiments. One is related to stimulated parametric dawn conversion. So in one of the optical tables, we have a setup doing stimulated parametric dawn conversion. And we always, most of the time, we use these SLMs, these spatial light modulators. So we deal with this transverse spatial degrees of freedom of light in most of the experiments that we do. And there's another optical table where we are doing spontaneous parametric dawn conversion. And in this case, we are using Gaussian orbital angular momentum light modes that we are trying to use this for quantum thermodynamics. That's the first topic that we'll talk about in more detail now. And there is also an optical cavity that is being the main guy in this setup is René Araújo, which is this young man there, waving. And there is this optical cavity that we built there. And we are trying to use this as a kind of mode sorter. Try to select optical modes like these ones here, like Gaussian with different orders, radial orders, and so on. So then let me start to talk about the first word. So the motivation is quantum thermodynamics. So sometimes it's hard to motivate quantum thermodynamics because nobody actually knows if this is really useful for something. But I think it's interesting to try to find connections between thermodynamics and quantum mechanics, and there are some common points, like the whole of information in these 2 theories. And then I just took 2 review papers here, and to inspire, to motivate the study of quantum thermodynamics. And it seems that the idea is try to understand how information can be useful in processes like thermodynamics, in which you can extract work from heat and from other sources of energy. We have had a few people here, few groups here in Brazil doing works in quantum thermodynamics. So I'll just pass very quickly in a few examples. So some guys doing NMR, nuclear magnetic resonance, right? So they are using NMR nuclear spins to do some kind of computation with these spins to represent thermodynamic systems with quantum properties. And they did many things. And like studying efficiency of heat engines with out of equilibrium reservoirs and so on, and studying the heat flow from the quantum perspective, and the whole of coherence in thermodynamics and non-equilibrium systems. So there are a few examples that I'm showing just to show that people is interested in the subject, and we would like to provide some experimental platform to address problems like these ones that some of them they are studying with only theoretically, and some of them are being studied with other physical systems. But there are very few experimental approaches to address these problems. Okay, so this is about the motivation. Things like studying Maxwell's demons and so on. Okay, so our first step in this field was the study of out of equilibrium system. In fact, it's a kind of fluctuation relation. It's about the so-called Jarzynski fluctuation relation. So I spent a few years to start to understand a little bit about this subject, because it's kind of complicated stuff somehow. But now I think I have a simple picture that can be useful to state the problem when we talk about out of equilibrium physics. And this picture is when you have classical thermodynamics. So the main physical system that everybody shows is, so then you have a gas, then you can compress the gas, then you can make work over the gas, or the gas expands and the gas makes some work. And if this process is what they call adiabatic, meaning that the evolution of this motion is performed through a series of equilibrium states. And so if you have this adiabatic evolution, a very controlled one, then all the work that is performed on the gas will increase its internal energy, or in the other way around, all the internal energy that the gas loses will be turned into work. So this is an important stuff, because you don't want to generate extra entropy. If you want to extract energy from heat, you would like to take all the energy from a heat source and transform it into work. And when you try to analyze the equivalent of the situation in quantum mechanics, then the picture is this one. You have a system with energy levels, which are discrete energy levels like this. And then if you change the energy gap, so the energy difference between these energy levels, and if you do it very slowly, so that the populations do not change, then you have the analog of this situation. So when you increase these energy gaps here, without changing the population, you do some work that is changed into free energy. And this can be done in the other way around. So you can take back the work by reducing the energy gap and not changing the populations. But this is never the case. In fact, this is never the case. This is practically impossible, or it's very hard to do in practice. So, but then if you change the energy levels very quickly, then the populations will change. And this is about this no-equilibrium stuff and this fluctuation relations. This is about this kind of thing. So knowing when you do a process of, for instance, changing the energy levels quickly, so do you have transitions from a ground state to higher energy level states? And then you would like to know what are these transitions and what are the impact of these transitions in the free energy. So how much of the free energy is lost when you do this thing? So this is the picture I have about this fluctuation relations. And then there is this relatively famous in this field, this no-equilibrium equality for free energy difference by Krzysztof Jarzynski, that was first obtained in the classical regime, and it relates work in a given process with free energy, and by this exponential. But then it was also translated into the for quantum systems, so it's valid also for quantum systems. This was done by Tazaki, and so the idea is to know for a given quantum system that you have a process, so how much of the work is transformed into free energy. So then some people started to be interested in testing this kind of fluctuation relation using some experimental scheme. Okay. So, but in order to test, so I would like to talk about testing this this fluctuation relation. So measuring the quantities that you have in this equation here, and realizing a real process on a physical system, and calculating these quantities from the measurement, and checking what's going on here. So in order to have this quantity here is this exponential of minus beta W, where beta is the inverse temperature, 1 over Boltzmann constant and absolute temperature. And W is the work, so work that you do on the system or the system does on the process. And delta F is the change in the free energy. So in order to obtain this quantity here, in a quantum system, you need to do the same process in your quantum system, and you have to measure the transitions. And for each transition, you will have some work. And then you have a kind of work distribution. And from this work distribution, you have the probability that some work is realized on the system. And once you have this function here, you can calculate this average. Okay. And in the right-hand side, this delta F, you can obtain by simply looking at the change in the Hamiltonian, because the free energy is an equilibrium quantity, and it depends only on the Hamiltonian of the system. Okay, and then we would like to do this using an optical system. This is already an issue because there is no mass, there is no gas, there is no temperature. It's a complicated stuff, but we think it's possible to study these problems using an optical system. And we would like to use this analogy between the paraxial wave equation and the two-dimensional Schrodinger equation. So to make a relatively long story short, we start from the Helmholtz wave equation, which is an approximation for a monochromatic field. And then we make the paraxial approximation, meaning that you have a light beam that propagates in the XZ, and this light beam does not diverge and does not converge too much. So it's more or less paraxial. This is the approximation that you must do to use this equation, and then it appears this complex part here, and it makes it analogous to the Schrodinger equation, and the analogy is made by comparing the amplitude of the field with the wave function and the time with the position in the propagation axis. So the propagation of the field is equivalent to the time. And then it's also possible to include the potential, so then you can have some kind of interaction. And then you can have the potential. It's like a single particle in a potential. And then this equivalence here shows that if you can create in some kind of medium an index of refraction that depends on the position, in this case, this is the transverse position. We recall that the propagation is to the z-axis. Then if you can create a distribution of index of refraction, then you can have the analogy, perfect analogy between these equations, Schrodinger and paraxial equation. Well, one solution for the wave equation, one solution for the quantum harmonic oscillator, in which you take this parabolic potential. So we know the solutions, they are the Hermite-Gaussian and Laguerre-Gaussian functions. And of course, we are interested in this problem because we can produce Hermite-Gaussian light modes and Laguerre-Gaussian light modes. But then by noticing that these are the solutions of the harmonic oscillator, we can write some Hamiltonian for the system. So this is the Hamiltonian of the harmonic oscillator. We can write in terms of the circular quantum number operators, which are this n here. And then you can write the energies in terms of the eigenenergies, in terms of the orbital angular momentum, this L, and the radial number P. Okay, and if you take the case where P is equal to 0, then you can see that the energies of this quantized harmonic oscillator are given by the orbital angular momentum. So that's what we want to do. We want to produce Laguerre-Gaussian beams and associate the orbital angular momentum with the energy of some quantum harmonic oscillator. Okay. So if you do this, we can test this fluctuation relations using light beams by doing the following thing. So you suppose that you have this harmonic oscillator with this Hamiltonian, and then you can prepare some thermostates for this system, recalling that thermostates are nothing more than diagonal density matrix where you don't have coherences, and you have these energy states that appear with probabilities that are given by this function here. And then if you prepare this thermostates, you can apply some process, and this process will induce transitions, and then you can try to measure the probability that this transition happens. So then there's a kind of protocol, they call it measurement protocol, for testing these fluctuation relations. It goes like this. Then you prepare a thermostat, but then you make a measurement and you project the state onto some energy eigenstate. And then the probability of performing this measurement will be given by the thermal coefficients. So 0 is the most likely to appear, and with exponentially decreasing probabilities. But then you prepare a pure state here, and then you apply a process. What is a process? For instance, in a harmonic oscillator, the process can be the change in the potential, so that the energy gap will change. The energy differences here will change. And then you have transitions. So you start from a pure state here and goes to a superposition of states. And then the Hamiltonian will be different because you change the potential. And then you perform another measurement here. So from these two energy measurements, you can calculate the difference between these two energies here. And then you can have this probability transitions. So you repeat the process several times, and then you can compute these probabilities. So for instance, you start with this state here, and then you end up with this one. In this case, the work was this energy difference. And this follows a definition of work, which is given by this energy difference. Even though there are some discussion about this definition of work, but it's used when you're dealing with this fluctuation conditions. Okay, so then you see that we can do this with light. Whether this is representing this harmonic oscillator energy wave functions and eigenenergies, but of course we can do the same in this basis of the orbital angular momentum modes, and then we can do the same. So we prepare initial states with some orbital angular momentum, we apply a process, and then we measure the final orbital angular momentum. So it's a simple idea. And from these transitions, we can compute the work distributions and compute the Jarzynski fluctuation relation, for instance. And one possible process, and the process can be implemented by SLM phase masks. So you prepare a light beam, you apply a phase mask, and then you measure the orbital angular momentum. Okay. So that's the idea. And then from these measurements, we can have these probabilities here, which are important to compute the work distribution. So this is the probability that you have a transition from an initial state with orbital angular momentum L to a final state with orbital angular momentum L prime. And this is done by this product. So the first term here comes from the thermal distribution. So what's the probability that given a thermal distribution, you project your system in this state with orbital angular momentum L. So this probability is given by this quantity here, where Z is the partition function. And this is the transition probability that we measure here in the experiment by preparing the state, applying a process, and measuring the final state. And then from this quantity, we can compute the work, so-called work distribution, and calculate this quantity here. Okay, that's what we would like to do. So our first attempt was just doing this experiment using a laser beam. So you can have a laser beam, a helium laser beam. Then you use a first SLM to prepare some orbital angular momentum light beam representing an energy eigenmode. Then you have a second SLM which implements some process. And then in this case here, we used a mode sorter to to measure the orbital angular momentum. In this case, we can repeat the experiment several times, and we can compute the probabilities that an initial state under the same process will end up in a final state here. And then I will go through this very quickly because I want to show more recent stuff. Then we did this calculation. We obtain a work distribution like this one here, and then we calculate this quantity here. And in our case, in this case here, the free energy did not change, and then this thing should be 1. So and then there was something nearly 1 due to technical imperfections. Then and these are the transition matrices. So this is the initial state, and this is the final state, and these are the probability distributions for the process that we use. Okay, so then I will go fast to this step here. So we would like to do this, but not with a laser beam, but with single photons. And then we realized that we could do a setup like this, in which we use SLMs and optical fibers. And in this case, we can make the remote state preparation of a single photon here in an orbital angular momentum, apply a process, and then measure the orbital angular momentum by projecting onto a single mode fiber. Then we started to deal with this setup. But we realized that there was this work here from 2013, which did exactly the same thing. But the only particularity is that the same setup, but they only used here process as a process, what we call now process. But what they did here was to apply turbulence masks, simulating Kolmogorov turbulence, and they measure the correlation between the orbital angular momentum from signal and idler photons. So then we realized, when I saw this thing, I realized that they did the experiment we would like to do, but for the particular case where the process is turbulence. Turbulence can be a process, right? And the very interesting one. Okay. Then I contacted Andrew Forbes, and then he kindly provided the data, and then we did an analysis of this data in terms of this Jasinski fluctuation relation. Okay, so these are this transition matrix that they obtained with these turbulence masks. Okay. All right, but then we need to understand a few things. Try to do it fast. To understand how can we interpret this experiment. Well, the experiment that Forbes did was to analyze the loss of correlation between orbital angular momentum between signal and idler photons when they propagate to turbulent medium. But now what we want to do is the following. So then we have pump laser, nonlinear crystal, parametric down conversion, and then if we perform a measurement here of the orbital angular momentum, and if we pump here with L equal to 0, we know that from the correlation, if we project here onto plus L, then the photon in the other side, if the signal is plus L, then the idler photon will be minus L, okay? Because of this correlation, so that the sum of the orbital angular momentum must be 0, the orbital angular momentum of the pump. So then this is the remote state preparation measure here, and I have a heralded photon with a given orbital angular momentum. Okay, and there's this Klitschko advanced wave picture that we like a lot, and it's very easy to understand transverse correlations here using this picture, is that everything works here like this thing here was in fact a light source that emits an advanced wave that propagates backwards, and then it transmits to the crystal, and then you have the photon here prepared with this orbital angular momentum. So if you have L equal to 0 coming out from the fiber, then you go to an SLM that applies a mask which transforms it into minus L. Then when it's propagating backwards, and then when it goes there, it will be still minus L. Okay. So then, because if it was plus L, you apply minus L, and it comes back to 0. So just must be careful, but it works. And then you can do this kind of thing in both senses, whether from here to there or from here to there, right? So then if you use this thing, you can analyze this turbulence masks as processes in this single photon with orbital angular momentum. Okay. But before we continue, just mention this work. We have this work posted at the archive, where we just showed that if you, for instance, if you take this signal dialer photons, and if you take one of them and you trace over the orbital angular momentum, I mean, if you use a bulk crystal here, a bulk detector here, then you prepare this state here in a thermo state. Because there was this work here from 2003 where they demonstrated that what they call the spiral bandwidth is something which presents an exponential decay, right? And this is just a matter of interpreting this exponential decay as a thermal state. And because we are making the trace over the orbital angular momentum here, the state there will be a mixed state. Okay? So then in this work, we just showed that this works as a thermal state. So then we can prepare thermal states of single photons and orbital angular momentum. And then using this advanced wave interpretation, we can have two things: whether we prepare a single photon with some orbital angular momentum here, and it propagates through the turbulence, and we measure it here, or the other way around. We prepare here, it propagates through the turbulence, and we measure here. And we can also have the other stuff. We can have turbulence in both sides, and then interpretation is you prepare the photon, it goes through this turbulence, free propagation, turbulence again, and then detection. And the other way around is also possible. Then, using this interpretation and these measurements obtained from the experiment, so the correlation, then we see that, for instance, for single channel turbulence, so turbulence only in one beam. So if you have no turbulence, this is a kind of calibration measurement, you have almost perfect correlation. So +5 goes to -5, +10 to -10, and so on. If you apply turbulence with a weak turbulence, then you disturb a little bit this correlation. And if you apply stronger and stronger turbulence, it disturbs even more, as expected. And for double-sided channel, I mean turbulence in both sides, you see that the perturbation is even stronger. Then from this from these measurements, you can compute this quantity here, this exponential of minus beta tau. And they should be equal to 1. But you see that they are not. And in particular, they are bigger here. For strong turbulence, they can be much bigger than 1. And this is not allowed, meaning that one interpretation for this fluctuation relation being bigger than 1 is that the entropy is being reduced. And then this is forbidden by the second law of thermodynamics. And then this happens for both cases, single and double-sided chain. Okay, then we try to analyze why these things are not equal to 1, and in particular, for instance, if they were smaller than 1, then we could say that this is due to technical imperfections because this increases the entropy generation. But as they are bigger than 1, you have some kind of decrease in the entropy generation. And then we discussed a few things. We were considering that free energy was not changing, but it's probably not the case. And heat generation, but it's probably not the case because there's no heat bath. And possible information exchange would also cause these things, but it's probably not the case. So the most probable source of these quantities being bigger than 1 is the way the turbulence is simulated, because it's not a unitary process. So you apply for each turbulence strength, you apply turbulence 30 different turbulence masks with the same turbulence strength. This means that you integrate over 30 sets of measurements, and this makes the system open, while this quantity is deduced for unitary or unital transformation. Okay. Then we found that this.
Paulo, excuse me, short question from Sergei Kulik. What kind of turbulence did you use?
Yes, the turbulence used is a Kolmogorov turbulence simulated by this SLM masks. Okay, so and the way Andrew Forbes did this was changing the scintillation strength and repeating the experiment several times and integrating over all measurements. Okay.
No, Paulo, I mean, is it just spreading of the angles? Is it right?
Sorry.
What happened with the beam? I mean, in experiment, is it just spreading of the mode? I mean, angular distribution you introduced, or something else?
Yeah. Well, let's see. Yeah, maybe the best on this.
Yeah.
So you know, it's possible to realize the turbulence and also realize the holographic measurement, where you apply these masks to increase and decrease the orbital momentum and couple to the fiber, right? Mm-hmm. So then when you apply the turbulence, what happens is that if you have some kind of, let's think, some orbital angular momentum state, it will couple the beam with other orbital angular momentum modes. That's what it does, you know.
Nice.
In fact, it perturbs the beam, it diffracts,
yes,
but then in practice, it diffracts. It couples different orbital angular momentums here in this side and this side. Okay.
Yeah. Okay.
Okay, but then we found this generalized Jarzynski equality, where you consider, instead of a unitary or unital process, you consider a quantum stochastic map. So the process can be a very general stuff, which is described by a quantum stochastic map, which describes open systems, right? And then you can, then in this new relation, you have this delta here, which measures the discrepancy between this unitary transformation and the general stochastic map. I mean, if the transformation is unital, you apply it to unitary or unital, you apply it to the identity, and the identity doesn't change. And then you can measure this delta is the amount that your process changed the identity, okay? Then you have this new configuration here. And then when you use this thing, it worked perfectly. So we calculated the difference, this new quantity here in the inset, which is the exponential average exponential minus 1 plus delta. And then we see that this explains perfectly, so the difference is 0. So this explains perfectly the situation, okay? This meaning that our process was not actually unitary nor unital. Okay? So then we also tested so you can obtain a kind of generalized version of the second law of thermodynamics, which is given by this thing here. And then we tested this, and we see that, of course, we are not violating the second law of thermodynamics when you take into account this openness of the system. Okay, so I'll take this last 10 minutes to talk about a different subject, and then if you want to come back to the previous one, we can discuss later. So this is about phase conjugation using stimulated parametric non-conversion. So, you know, phase conjugation is a very old subject, but it's a very different, very interesting one, because it's about time reversal, right? So then, for instance, if you take a wavefront that is propagating like this, diverging, and is reflected in an ordinary mirror, it still diverges, right? But then, if this beam is reflected in a phase conjugation mirror, then it comes back. So it's the time reversal of the beam, right? Then this was studied a lot in the 80s, right? When they discovered the laser. But then there is the phase conjugation of the polarization state. How the phase conjugation of a polarization state is manifest. For instance, if you have circular polarized light like this, right circular polarized light, and it reflects in an ordinary mirror, then it comes out as a left circularly polarized light. So there's this reversion here. But if it is a vector conjugation mirror, it comes back with the same polarization state. So this is the signature of the phase conjugation. And now what we thought about was, what about doing this with this vector vortex beams, which are light beams that have polarization distribution in the transverse plane, right? So this is an example of vector beam in which you have a distribution. You can have a circular polarizations here, elliptical and linear and so on. And then you will notice the conjugation as a difference between the reflection between a regular mirror and a phase conjugation mirror. Okay, this is the subject here. Well, before we did that experiment, it's a relatively simple experiment in concept, we kind of elaborated this notation here because we used this two crystal source in parametric Down conversion. So if you have this two crystal source, it's very often used to generate polarization entanglement. Okay? Then you pump these two crystals, and then you have this entangled state like this, VVHH, and then from this you can generate every Ribeiro state if you want. Okay, but then we take the source and we stimulate the emission with another laser. Then we stimulate the signal. Then when we stimulate, we kill the entanglement, of course, but then the ideal beam will be indirectly stimulated, and then it will take the polarization properties, which depend on the phase matching here as well. And if we do this with two crystals, then we can stimulate any an arbitrary polarization state, including circular and elliptic and everything. So then we just wrote in a different notation here, which allowed us to define parameters which are compatible with this how is the name of this thing?
Stokes vector.
Stokes vectors, yes. I just forgot. Thank you. So we can write this Stokes vectors in this in terms of these parameters, which comes from that conversion state, and then we can realize what's the signature of the phase conjugation in this case. So in general, the phase conjugation appears when you change the sign in the third element of this vector here. Okay. And is this kind of thing here. When you change the sign here, you have the phase conjugation of this polarization vector. Okay? But then what we found is that when you have this stimulated parametric Down conversion with two crystals, this conjugation depends also on the polarization state of the pump. So when the pump is polarized the diagonal, you have the ordinary, the usual phase conjugation. But if it's anti-diagonal, then you have the change of the sign in another component of the vector. Okay, and then it's a kind of well, we would not say it's phase conjugation because the phase conjugation depends on the basis, right? So, but it's an effect analogous to the phase conjugation, which appears by the change in the sign of this component here when the pump is anti-diagonal. And there's also an interpretation in terms of the Poincare sphere, which is a reflection. So the phase conjugation in terms of the Poincare sphere can be seen as a reflection around a mirror reflection around some plane. And this plane depends on the polarization state of the pump. Okay, so that's why you see that in this case here, when you pump like this, the plane is a vertical plane here, and when you pump like this, it's a kind of horizontal plane. In fact, you can tilt this plane by changing the pump. Okay, just this is vector phase conjugation in stimulated parametric Down conversion. You'll notice that it's not a mirror. It's both stimulating beam, seed beam, and its phase conjugated. They propagate the same planes, right? It's not a mirror, but it produces a copy of this polarization state, which is a phase conjugation of an arbitrary input state. This is the point. And you can change the pump to control this this phase conjugation, which can be geometrically interpreted in terms of the Poincare sphere as this reflection around this around the plane in the Poincare sphere. So these are some results, and that we show that they are good enough. But then, if we do this with beams which are polarized in pure states of polarization, in plane wave polarization states, plane wave like, we can do the same for this vector vortex beams. That's what we did, just to show very briefly the results. We show that we can send this kind of vector vortex beams with several kinds of polarizations, and then we observe its conjugation, which is you see the change in the sense of rotation of these polarization states, which are not linear. And the one way of showing the results is by projecting onto HV, diagonal, and circular bases. Okay, and the signature of the phase conjugation is given by this orientation of this diagonal projections here. Okay. All right. This is just another work in which we build up a theoretical description of this process in simulated parametric down conversion in terms of vector states and density matrices. And we also present here a kind of geometrical representation for phase conjugation of vector vortex beams, which are, of course, more complicated than the previous one for plane wave light beams. Okay. Okay, so I come to the end, the conclusions. So what we are trying to do is trying to use these light beams to apply in some experiments to study quantum thermodynamics. In fact, much more fluctuation relations. In order to really go to quantum thermodynamics, we still need to demonstrate that these light beams can work as thermodynamic systems, which require some kind of interaction that maybe it's possible. We are trying to find out how, and some of the possibilities of using this kind of things is this idea of converting information, showing the conversion between information, work, heat through this heat engine. So, is it possible to build optical heat engines? This is one possibility, and also this the use of this stimulated parametric down conversion with two crystals. We think that is interesting because it allows us to explore this more complicated light beams. I think that the terminology which is more interesting is structured light beams, because some light beams with different polarizations in the transverse plane, they are not vector beams, they are not vortex beams. So then you can have these structured beams. Okay? And then we think that this is a possibility, is a simple setup, and that's we are trying to do. So finally, thank you. Looking forward to having you in Floripa soon. Thank you.
Thank you very much for a good talk. And so now, please, questions. So you may raise your hand. And I think the first question from Sergey.
Paulo, much for the nice talk. But the question is the following. So, am I right that you somehow introduced some sort of links between quantum thermodynamics and entanglement with by photons. But the question actually is, can you predict some new effects just while studying the entanglement with photons? I mean, new effects in quantum thermodynamics.
Mm-hmm. Yeah, good question. Is a question that we have been asking ourselves. But well, first point is about entanglement. You know, I don't know how to use how to connect entanglement with quantum thermodynamics. What we found out that can be useful so far is using entanglement in order to perform this remote state preparation. And this helps in avoiding part of this protocol to testing these fluctuation relations, in which you would have to measure the system itself to make the first step, and then process, and then another method. So by using remote state preparation, you can skip one part of the protocol, and you can have single photon states, heralded single photon states, meaning that you have a very authentic quantum system that you can test under thermodynamic conditions. But the second point is, can you do something really nice with this? Trying to predict some new effect, something that you cannot calculate easily,
exactly.
right? So this is a good point, and in my opinion, for instance, that's why we were trying to do this test with turbulence, because turbulence, it's very hard to describe analytically, right? So then you can, of course, you can do it in a computer simulation of turbulent process, but at least you cannot describe analytically a process implemented with a turbulence. This is, I think, it's one step towards doing something really new. But the ideal, it's something that we'd like to do. The ideal would be trying to realizing how to make an experiment in which you observe something that was not predicted even theoretically, right? But we don't know how.
Thank you.
Okay, so the next question from Professor Ma, please.
Hello, can you hear me?
Now I can
Yes.
hear you.
So thank you, Paulo, for this very nice talk. And I believe most of us are tempted by your last slide. Beautiful view. I have one question. During your talk, I was dropped offline for a few minutes, and I believe I missed the most important part. In your first part of your talk, you talked about the unitary process between two different harmonic oscillators, and you changed the shape of the potential in order to realize this adiabatic transformation. So my question is, what is yes, exactly, this is one. So what is direct connection between this picture with respect to your transformation implemented with SRM?
Okay, so thank you, Chalson. So, well, I think that the idea of this slide is to illustrate what, in general, one is interested in doing this fluctuation relation studies. So one possible process that you realize in a system, for instance, a harmonic oscillator, is this unitary and a sudden process in which you just change the potential, right? In this case, the process itself, it's very funny because people says the process is the identity, but what happens is that you change the Hamiltonian, and then the transitions are given by the overlap between the initial wave functions and the final wave functions. Okay, and this is what happens here. But in our case, this is not what happens, because in order to change the Hamiltonian in this analogy, we would need to change the geometry of the mode. I mean, the diameter of the family of modes, you know. Right. This is equivalent of changing the Hamiltonian. And in fact, we didn't do this. In fact, we could do this. In order to do this, we would need to find a way of performing the projections in the Laguerre-Gaussian basis for a different family of modes in comparison to the initial one. Okay, but what we do is that the Hamiltonian is the same, so there is no relationship between this and this. The Hamiltonian is the same, but there is some process which couples initial states from the same family, initial states to final ones. Okay, how can we see this process in terms of this picture here? It's something like, for instance, you take the first Hamiltonian, and then you suddenly open the potential, and then you come back, so that you end up with the same Hamiltonian, but then you induce transitions. And I think that the turbulence does exactly this thing. So it's like you change the Hamiltonian, comes back very quickly, and then you induce transitions. But you know, you can do this in a unitary way, for instance, using a spatial light modulator. Right. But in fact, the experiment was done in a different way. So it was not unitary because there was a sampling over different masks, and this resulted in destroying the coherence that were there eventually. It's kind of opening the system.
Right. You mentioned that you sum up like 30 different masks to create this mixed state, right? That's what you have said.
Yeah.
Okay. Yeah. Understood. Okay. Mm-hmm. Okay.
Okay, Stanislav, please.
Not hearing.
Oh, sorry, I forgot to switch on the mic. So the question was, can you really simulate an adiabatic process in this analogy, and what would be like the analogy of an adiabaticity parameter?
Well, I don't know. I don't know. The question is, the answer is, I don't know. I think it's in principle it's possible, because this analogy allows a great deal of control of the system. So I think you can engineer evolutions of phase masks and everything, so that the evolution would be adiabatic in the sense that you do not change the population, right? But even if we can do this, I don't know if it would be interesting. Maybe you can take, for instance, One adiabatic transformation would be simply an expander. You take your Lagrange-Gaussian beam belonging to a family of modes and you expand it. And then you go to another family. And then it's adiabatic because the population would be the same.
Mm-hmm. I see.
Paulo, may I add a comment on this? While you were talking, I was thinking of a tapered fiber, of changing core size, changing very slowly. You can imagine that in this intermediate region, there's an adiabatic change in the beam parameter. Maybe that's a way of doing it.
Okay, I see. And if you take a multi-mode fiber, for example, with a slowly changing parameters, or I don't know, like which is bent with a large radius, that would also correspond to adiabatic evolution or not. And so you can apply this theory to predict something.
Your comment makes me think about the real the approach we are using does not explore very well the analogy between the paraxial wave equation and the Schrodinger equation, because the best way of exploring this would be having some kind of medium with a controlled index of refraction. That would really simulate the harmonic oscillator. But what we do is kind of what we call this stroboscopic operation. So we generate the beam using the SLM, and then we do something in a plane here that changes it, and then we have some evolution to another plane. So it's a kind of stroboscopic in this sense. So I just look at the evolution at certain times, and during these times, the beam obeys some kind of Hamiltonian. But the best thing would be think about a kind of a piece of glass, and then you can modulate the transverse index of refraction, and you really change the potential. That would be great.
Yeah, I think a multi-mode fiber can do that. And I also have a more like philosophical question. Is there any reasonable generalization to non-thermal states? Because this all applies to thermal states only, right? With no coherence.
Well, there are some studies in which people use states that are not thermal and states that have some coherences for quantum thermodynamics stuff. So one of the things is, for instance, if you have a heat engine, some people, instead of using the heat baths, actually being heat baths, they use out of equilibrium heat baths. Like, for instance, if the thing is optical, you use heat baths which are squeezed states, squeezed heat baths, and this gives you some improvement in the efficiency of the heat engine and so on. But from the point of view of fluctuation relations, I think you need to deduce a different fluctuation relation, which takes into account that you are not, the input state is not a thermal state. And if you do this, you kind of lose the connection between thermodynamics and this stuff, And then, for instance, I've seen recently some paper, I forgot who was, but I think I can have the reference, in which the guys, they try to measure the transition probabilities by using some POVMs, which allows them to measure the transition probabilities without making the projections. So in this case, you can have initial states with coherences, and then you can measure what's the probability that it ends up in a given final state for a given process without destroying the coherences. So, but you know, I don't know if this brings something useful. If I mean, in terms of if the work is if you can extract more work from a given process, for instance. Okay.
Thank you.
But this is the kind of thing that people are trying to find.
Okay, thank you. Ranjit.
Thank you for your informative presentation. I have two questions related with your last part of presentation. So the first one is for phase conjugation, if I am correctly understood, you are using Chi2 nonlinear medium as compared to Chi3. Are there any specific reasons behind that? The second one is you are using two crystals placed sequentially. So for what purposes second crystal is used? Thank you.
Thank you for the question. Well, the first answer is, you know, we've been dealing with the system for a long time, and then we did stimulated down conversion long time ago, and in the beginning we used it to perform alignments, you know, because they have stronger beams, it's easier to align, etc. And then we realized that it is the phase conjugate of this guy. So then there is nothing really special in terms of phase conjugation. Why we are using this is the opposite. We found that this is able to produce phase conjugation, and then we are trying to explore this phase conjugation. And then from this point of view, one motivation is that you can have a phase conjugate beam with different colors, different wavelengths. And this may be an advantage or a difference with respect to the four-wave mixing, for instance. So most of the people use four-wave mixing to produce phase conjugation mirrors, right? And the reason why we are using two crystals is very important one, because in this kind of crystals we have the phase matching, type 1 phase matching, for which, for instance, in crystal 1, if you pump with a vertical pump, then you produce horizontal polarizations for signal and neighbor. Then, if you take a second crystal and we rotate this crystal with respect to the first one, then we can pump it with the horizontal polarization and generate vertical polarizations. So if we combine these two emissions coherently, meaning that the coherence length of the pump crystal is bigger than the distance between crystals, then we can have all possible polarizations here. So if I pump diagonal, I can have a diagonal state here and there, or anti-diagonal, or circular, and so on. And our purpose here was even a bit more complicated, which is a structured beam that we stimulate, and the stimulated and conjugated beam should be structured as well. This is just a convenience.
Thank you. Because in Chi3 we do not care about the phase matching, but in Chi2 we have to be very careful with the phase matching. So that is why I just wanted to know. Thank you.
Thank you. Stanislav, please.
A bit silly question. So is this phase conjugation also a thermodynamical time reversal? So if you replace your turbulence channel with the phase conjugated mirror, will your, I don't know, all the thermodynamical quantities which you described in the first part will also sort of come back to the initial?
Yeah, you know, this is a nice question, because, you know, in the 80s, when people discovered the phase conjugation effect, the first thing that they did was to send a light beam through a turbulence, real gas, something scattering, and then sent to a phase conjugation mirror and back to the turbulent medium. And then you saw that the propagation backwards compensated the turbulence effect. You know, you can correct turbulence effects by using phase conjugation mirrors. And they even proposed and realized lasers in which one of the mirrors in the cavity was a phase conjugation mirror in order to have a perfect mode, spatial mode of lighting. So that the distortions can be corrected by the phase conjugation. So then the phase conjugation effect for the transverse profile of the beam is really propagation backwards. You know, it's like propagating. In this case, in our case, propagation is propagating forward, but the diffraction is like you propagating through minus t. So the time you have resurrection, right? But then what's the connection of this with thermodynamics? Well, I would like to connect it with thermodynamics. That would be very nice. But I mean, so far, the only idea I had is it looks like correcting turbulence stuff, you know. And from the thermodynamics point of view, there's one problem that all of these effects in phase conjugation, it's very hard to have high efficiencies. And then if you have very low efficient, the part of the beam that you correct is small. So that in terms of entropy, the reduction of entropy that you have is very small. And then I don't know if it would be possible to observe nice effects in thermodynamics, like reducing the entropy, you know, kind of Maxwell's demon that you can correct. You can evolve back in time, and in this case, if you evolve forward, you increase the entropy. If you evolve back, you reduce the entropy. So that would be nice, but I don't know.
Okay, thank you. If I see correctly, there are no more questions now. So thank the speaker. Thank Paulo again, and for a very good, very interesting talk. And see all of you next week the same time. So Professor Ma, will you tell us, are you ready to give a next talk next week?
Same time.
Yeah, look forward.
Okay, okay, so see you. Thank you, thank all of you for participating of our seminar.
Bye-bye.
Bye.
Thank you.
Thank you,
Paulo.
Thank you.
Bye-bye.
Thank you.